chapter 8 here. And again, I always hate these first chapters because it's more on theory and stuff like that. The AC, and if you're in digital, we'll talk about your clock signal using the oscilloscope here today too. Sidetrack here. Let me. All right, so what we worked with the last 8 weeks was DC, which stood for direct current. That was always a constant voltage. So if I were to when I put my voltmeter on my circuit and stuff, it constantly read 5 volts. That means that voltage always, was just basically just a straight line. It was just, staying at 5 volts. It didn't vary in voltage or anything like that. It was just a constant 5 volts. When we're working with AC, what we have is a signal now that's varying our voltage. It's going up to a positive voltage, and then it's crossing our 0 volts reference, and then it's going down negative, and it's changing directions as it's doing that. So either our voltage or our current is going to have polarity. It's going to be for what we call one complete cycle, is where it's from the time it starts to the time it starts to repeat itself. It's going to be one cycle. And there's 2 alterations within that one cycle. It's going to have a positive voltage or a positive current, and then it's going to switch directions, and the current's going to switch directions, and it's going to go in the reverse direction. It's not going to go in the reverse direction. It's just going to change directions. So that's what our AC signals are going to look like. Instead of being just a straight line, it's going to be a waveform. This is what we call a sine wave. There's many different types of waveforms that we're going to be working with. The sine wave is our most common one that we're going to be using. But there's also square waves, triangle waves, square waves, sawtooth waveforms, all different types of waveforms. Now, one thing about AC is that AC can do a lot more for us than what DC can do. DC is very basic. It can only do a couple things. What our DC voltage is basically to power up our circuits, or we can light light bulbs. But we can't do anything more than that with our DC voltage. If we want to transmit any information, we have to use an AC waveform. If I have for example, like if I have a radio antenna, and if I just put in a DC voltage into an antenna, I'm not going to get anything out of it. It's not going to send any signals out through it. What I have to do is I have to vary the voltage up and down before I can transmit any type of information. So like all our radio waveforms and stuff have some form of a waveform that's being transmitted up through the antenna. So AC is where it really becomes where we're actually capable of transmitting information either through a wire or wirelessly. And then DC is just going to be used to power up our circuits. We can light light bulbs with it and stuff like that, but it can't transmit any data. There's other types of AC stands for alternating current, and that's kind of a vague term because we kind of put in other stuff into that same category. A true AC signal is going to alternate the current. It's going to go in one direction, then it's going to cross 0, and then it's going to switch direction and go in the other direction. Now, if you're already in digital, Tom's got you hooking up hooking up a clock pulse. And that's just basically a square wave. In all our digital circuitry, it doesn't want to see a negative voltage or a negative current. It all wants to be positive. So our 0 volts reference is located at here, and then our clock pulse is going to go up to a positive 5 volts. So this isn't really a true alternating current because it never really changes direction. It varies the voltage. It goes from 0 to positive 5 volts. It goes from positive 5 volts back down to 0 volts. And it turns that on and off. It's like having me take a toggle switch or a light, switch, taking a DC voltage going into it, and then turning on my switch and turning it off, turning it on, off. And I can do that, and the faster I do it, that's going to be considered what I call my frequency. So even though this isn't really a true alternating current, we still put this into our AC category during our theory of AC. What it really is what we call it is a pulsating DC current. Okay, it's just a pulsating DC current because we're just turning it on. We're going from 0 to plus 5 volts, and we're turning it on and off. And so we'll take a look at the square wave here. I know that some of you in digital are trying to figure out how to get your clock pulse out, and then also how can I take a look at it, because it's too hard to look at, especially depending on the frequency. We can't see this on a digital multimeter. We can't see what the clock pulse is. So what we use in AC is an oscilloscope. So our main tool that we're going to be using in this class is going to be our oscilloscope. And what it's going to do is give us a graphical representation of our waveform so we can see what's going on. We're not going to be so much worried about the voltages like we were in DC, where we really wanted to have an accurate number. We wanted to make sure that we measured our current accurately. What we're really concerned with is making sure that it's getting up to approximately the voltage that we want, but what we're really concerned with is what the waveform looks like. And we'll take a look at that either, we'll get you guys so you can do it for your digital circuit, but then we'll look more in depth into the oscilloscope tomorrow. All right, so this is our AC waveform, and then when we're doing our circuits, instead of before we had our power supply that looked like that. That was our DC power supply. Now what our power supply or our AC source is going to look like is just a circle with a representation of the sine wave on there. If it's if we want to have a triangle wave, then you'll see that in your diagram. It'll show you that it's a triangle wave. Or if it's a square wave, you'll see the square wave in there. And our main tool that we're going to be using for generating these signals is going to be our function generator. So we can have function generators, we can have what we call arbitrary waveform generators where we can make up our own signals. But the basic one is they're going to be our function generators. We have both the lab bench style ones that you see here. They're all digital. And then we also have it on the MIDAC. Now, we're going to really find out the limitations of the MIDAC when we get into AC. Even though the MIDAC is a very useful tool, it's very limited on what we can use for measurements and also outputting certain frequencies. So we're going to have to use, in some of our labs, we're going to have to actually use the real function generator. What's that?
Real deal.
The real deal, yep. So this thing here, what's this one can go up to? I think this one can go up to 10 megahertz. Yeah, so this one here can go up to 10 megahertz. So 10 megahertz represents a frequency. It's representing how many times it completes one cycle. So, for example, one complete cycle is from the time where it starts to the time where it ends, or right where it starts to repeat itself again. And that's going to happen And so when I say 10 megahertz, what that represents is that that signal is going to go up to a positive voltage, go down to a negative voltage, and start over, and it's going to do that 10 million times in 1 second. Okay? So pretty high frequencies, but that's still, 10 megahertz nowadays is really considered even slow.
That's gigahertz.
Yeah, we're into gigahertz and quite a ways up into the gigahertz now. So which is a billion times. So our MIDAC is going to be kind of limited on what we can do because the MIDAC, it utilizes our sound card to generate our signal. So sound, as I'm talking and stuff, if I were to put it on an oscilloscope and I start talking and stuff, my frequency is going to change and my amplitude is going to change as I talk. And my voice would look something like this. Well, I can duplicate this same signal if I want to. I can take this and I can generate a nice sine wave out of my sound card. And that's how we get our function generator out of our signal. We just go ahead and we create a sound wave, but the sound wave looks like a nice sine wave. And then since it's using our sound card, we're only capable of going up to 20 kilohertz. So we can go from about 1 hertz or 10 hertz to 20 kilohertz, because that's the audible range of our hearing. And that's all the sound card's able to do. And that's what we also call, what we call on our, like if we're doing something with audio amps or chips, is what we call, that's our kind of our frequency response, meaning that at 10 hertz, I can get a nice signal, but after I get up into the higher frequencies, my components are going to have a low frequency response. It's going to have a high frequency response, and the signal is going to die after I go up to 20 kilohertz. But we'll get more into that as we go through the class here. So we do have the function generator on our MIDAC. We have the oscilloscope on the MIDAC, but that's going to be limited, and we're going to sometimes have to use the real equipment on our workbenches to complete some of our labs. Plus, it's a good way of getting used to using our labs. All right, so we kind of talked a little bit about the alternating current using our AC source. So when I'm looking at it, and this is how so when we're trying to analyze the circuit, we also do it the same way. We have one complete cycle. We have our positive alteration, and then we're going to have our negative alteration. And when we're analyzing these circuits, what we do is we don't look at it as one complete cycle, because that would be too complex. We'd have way too many things going on at one time. So what we're always doing when we're trying to analyze the circuit, we're looking at our positive alteration, and then our second alteration. So my first alteration is going to be positive. So my polarity across my function generator is going to be positive, negative. And again, just like we did in DC theory, our electrons always flow from negative to positive. So my electrons are going to be coming out of my negative side of my source. It's going to go across my resistor. My polarity across my resistor is going to be negative, positive, and then it's going to go back across my source. Then on my second alteration, now as it goes and crosses zero and starts goes to my negative alteration, what happens is that my polarity across my source now is going to change directions. And that's going to go positive, negative, and this time now my current is going to go this way. And put the polarity across the component, and then back up. So that voltage across the resistor is always going to be changing polarities. It's going to, if I put if I were to have this as a low enough frequency where I could see it on my digital multimeter, I put it on there, what I would see on my digital multimeter would be my multimeter, my voltage would start to slowly increase, and it's going to peak out. And the voltage is going to start to slowly decrease. It's still going to be positive, and it's going to start to decrease. And then once it crosses 0, my voltmeter would read 0 volts. And then, so right now, let's just say I'd be reading a positive 5 volts on my digital multimeter, and then it would start slowly ramping to the negative. And all of a sudden, my voltmeter would start reading negative voltage and peak out to a negative 5 volts. And then we go up and then until it got to 0 again. Well, if I do that really fast, my multimeter won't be able to see that. So we'd have to use an oscilloscope to get that graphical representation. But if I'm measuring my voltage across my resistor, it would look identical since I only have one component in there. That component is going to drop all the source voltage. And on my oscilloscope, I would see this same kind of waveform. Now, since this is happening, these polarities are switching back and forth across my component. When we're talking about AC, we're not going to use polarities other than when we analyze the circuit. And we're really not going to be analyzing the circuits until we get into solid-state devices. That's where when we get into solid-state devices, that's where I need to watch my positive alterations and my negative alterations. Because when I go into a solid-state devices only work with one direction. They only allow, depending on which way my solid-state device is in my component, is that it might only allow my positive AC voltage to go in, and then it'll reject anything that's going negative. So I actually can change up my waveform by using solid-state devices. And so at that point, we're going to really be focusing on looking at the first alteration, and then what happens to my circuit when I go to the second alteration. So when we're working with our circuits here, until we get into solid states, there is no real polarities because these things are switching back and forth. And so we don't really have to put in polarities. We already know that polarity across that component is going to be switching back and forth. So we don't have to worry about polarities on our going across our components. All right, any questions so far? Yes, I knew you would have a question. You every AC time,
First of all, these are
time
electronic
AC.
technicians. They're not electricians. All you got to say, touch it, it hurts. That's it.
That's right.
End of semester.
Yeah.
What's wrong with you?
I know. Gee, it's crazy.
I'd rather be working on their digital today because I'm sure 3/4 of them don't have it done.
I've been getting a lot of questions.
Yeah, what do you think that I'm right on this
Yeah, he can. That's why I said he likes square waves. On.
Square.
Yeah. All right. So let's look into a little bit more into our sine wave. Now, one thing about AC is that when we had our if we had a power source, and all we called it was 5 volts, okay? We didn't have any units other than it was 5 volts, okay? What it really actually represents is that it's 5 volts DC. Now when we get into AC, now we have a lot of different units that we have to keep track of because we can describe these waveforms in many different ways. And I actually ended up giving you a little cheat sheet there that you want to keep handy. Find mine. So on your little AC notes there, which I would keep handy, there's a couple things that, the first thing is that there's 5 things that we want to know about a waveform. And that one goes along with this sheet here. So keep this sheet handy, because when you're graphing, every time we graph, we want to know, when we're graphing out a signal, I want to know the 5 things about the waveform. So the first thing that we want to know about the waveform is that we want to know what it is. What's the wave shape? Okay? So the wave shape is this one right here. So that's going to be our, what we call this particular waveform is our sine wave, or our sinusoidal waveform. We just call it the sine wave for short. And so that's going to be our wave shape. It's going to be a sine wave. If all the time we're looking at a signal, we'll call it a triangle wave. So we need to know what type of wave shape that we're even looking at. The other one that we need to know is our amplitude. Okay? How large is it? How far does it go to the positive voltage? And how far does it go to the negative voltage? And we also, we're also going to be looking at it as, this is my V max, and this is my V min. And then we're going to be looking at time. How long does it take for it to complete one complete cycle? That's going to be our period. That's going to be how long did it take just to complete the one cycle? Then our DC references is going to be, where is this AC signal riding on? So for the most part, most of our signals are going to be riding at 0 volts. It's going to be riding right on our 0 volts DC. But I can go ahead and I can superimpose a DC signal onto this thing. And if I have a 5 volt AC signal, and I have this thing set at make it extreme. If I have a AC signal superimposed with a DC signal, what's going to actually happen now is that my AC signal is going to be running on my 10 volts DC. Okay? So I'm going to have 5 volts going positive and 5 volts going negative. So what happens is that now my AC signal, my amplitude for this particular one, is going to be going to a positive 15 volts and then going down to only a positive 5 volts. Okay? So it never changes direction, it never changes alternating current, it never changes polarity, right? But it's just varying the voltage between a positive 15 volts down to a plus 5 volts, but we still consider it an AC signal.
So it's like using a potentiometer, not going all the way down.
That's a good example, yeah. Yeah, so if I took we'll use that example. Instead of potentiometer, we'll use our power supply. So what Nick is saying is it would be like me taking my potentiometer and varying my potentiometer up and down. Or it would be the same as me taking my DC voltage supply here, setting it for a 10 volts reference. So if I set my thing at 10 volts, and then I go ahead and I turn and at my 10 volts I go 5 volts below, 5 volts above. And if I sit there and keep on going this back and forth, just like this with my potentiometer on my power supply, I would generate this signal. So it's just varying DC power supply would just be sitting there. And you can go ahead and you can hook it up to the oscilloscope, and if you vary the voltage going like this, just your natural reflexes of doing this up and down, you'll get something that's very similar to an exact sine wave, just by your natural instinct of going up and down, up and down. Once you get up to the seat, you're going to reverse it, go around, start turning it down, and you'll end up getting that same signal as what the function generator does. All right, so that's going to be our DC reference, and we're going to talk more about this more in detail as we go through and stuff. And then the other one that's going to be our fifth one that we want to know is what's our phase. Okay, so if we really analyze an AC signal, basically what it is, it's just basically a circle. If I were to take this waveform, and I kind of brought it back. It doesn't look quite, I mean, it looks more like an oval, but it's actually a circle. If I take a circle and I vary my voltage up and down, and I do that for 360 degrees or one complete cycle, I would really actually form a circle. Now remember when DC I said that everything that we do, nothing is instantaneous. Everything has a certain amount of time. Everything is based off of time. And so that's how we end up getting our AC waveform, is because I can't vary my voltage instantaneously. I couldn't be instantaneously being at 0 volts and 5 volts at the same time. So I have to give it a certain amount of time. And that amount of time is what we call our period. And so this phase, the fifth one there where I'm talking about is the phase, is where we start at. You know, we're going to start out at 0 degrees, and then we're going to go up to 90 degrees, then 180 degrees. You know, we're analyzing this thing from 0 to 360 degrees. And we'll talk more about phase 2, and then when we get into chapter 9, in chapter 9 and 10, then we're really going to be talking about phase shifts and stuff like that. We're going to be seeing more than one sine wave on our oscilloscope when we're using it, introducing it into an inductor. Okay? So those are the 5 things that we're going to be looking at when we're looking at these waveforms here for this chapter 8. Alright, so the first one that the book talks about is the period. So the period is, I think, did I put, yeah, so on the bottom there where it says down by the definitions, it says period. Time for one complete cycle. Okay? So here's our one complete cycle. And then the amount of time it takes for me to start at, we'll say at 0 degrees, vary it up to a positive voltage, go down to a negative voltage, and then back up. And at this point, this is where my waveform is going to start to repeat itself. Okay, so this one in green, that's where it repeated itself. So when I'm looking at the period, how long did it take to complete the one cycle, I'm looking at from the time that it started to the time that it ended, and it starts to repeat itself. And I can do it anywhere. I can go from, you know, I can do it from where it crosses 0. That's what I normally do. Is it's a lot easier to do it right at my 0 crossing. Or I can go from my peak to peak, and I can go from my negative peak to peak, anywhere where it starts to repeat itself. If I start from here, you know, my signal's going to start to go down, it's going to go back up, and then at this point, it's going to start to repeat itself, just right where it started here. That's going to be my period. How long does it take to complete one cycle? So now if we're looking at here where they have 3 cycles, we got the start of the first one, goes up, goes down, repeats itself. So that's the start of my second cycle. Goes up, goes down, repeats itself. And that's going to be my start of my third cycle. So those are my that's going to be my period. How long does it take to complete one period? So we kind of talked about, so on page 332, on figure 8-7 there, they're showing you all the different ways that you can measure your periods. Let's go there. So again, like I talked about, you know, I can go from my 0 to 0, that's typically what I do. I can go from my peak to peak, or I can go from my negative peak to peak, just like we talked about. So looking at this figure here, how many complete cycles do I have here? Yeah, I got 2 complete cycles on that one. All right, so then once we know what our period is, so for example, if I'm looking at, our most common use of AC signals is coming from our wall outlet. Okay, that's going to be 120 volts AC. So if I got, here I got my power plant that's coming into my wall outlet, and we'll use it simulate it as a function generator. And now, just like we were doing in DC, this resistor here, that's just representing some type of a load. This thing could be, a toaster oven, a light bulb, your TV, or something. It's just representing some type of a load. So when we're looking at our AC voltage, what we're looking at is that we're looking at 120 volts AC. We have to have when we were in AC, we have to have all the units for AC. Unlike DC, where we can just call it 120, if it was 12 volts, we just call it 12 volts. And then just assume that it's DC if I don't have any units. When I'm working with AC, I have to talk about all my different units. So when I'm talking about 120 volts AC, that's going to be my voltage, and it's going to be at 60 hertz. Well, 60 hertz means that this voltage across this thing is going to change direction 60 times in 1 second. So basically, if I would put my oscilloscope on it, I'd look at a signal, and this thing would go up and down, just like this. It's going to go up and down a certain amount of time in 1 second. So when I'm looking at 60 hertz, what it's doing is it's doing this 60 times in 1 second. It's going up to a positive voltage, going down to a negative voltage, going back up to a positive, negative, and it's going to do that 60 times in 1 second. So that's what my frequency is. If I increase my frequency, now let's say I change this, I'm changed it to 120 hertz. What it's going to do now is it's going to take that frequency and it's going to do it 120 times now in 1 second. So now my frequency, in one time, I'm going to be changing that direction of that signal twice as many times in 1 second. So my frequency is going to increase. And our frequency then is inversely proportional to our time. So if I know how long amount of time it took for it to complete 1 cycle, I can calculate out what my frequency would be. So for example, if I have 60 hertz, so if I have 60 hertz, my frequency, my time, my period is equal to my 1 over my frequency. And make sure you use the small f for representing your frequency, capital T for your time. So if I have 60 hertz, and I use my inverse key on my calculator, so take 60 hertz and do the inverse of 60. Everyone know what their inverse key is, because we're going to be using that a lot in AC. So what do you get for the inverse of 60 hertz?
.67 milliseconds.
Yeah. So what it's telling me is that that's going to be my period. So that's going to be considered for 1 complete cycle. What it's going to do is it's going to go from my 0 volts, here's my 0 volts, by 1 complete cycle. from here to here, it's going to take 16.67 milliseconds to complete one cycle. That's going to be my period. That's going to be my time for it to complete one cycle. Okay? So then if I multiply that by 60, then I go back to my frequency. So my period is just the amount of time it takes for one complete cycle. Then if I want to find out what my frequency based off my time is, then I can do the same thing. Then I can just do the inverse of 16.67 milliseconds, and that would tell me my frequency. And my frequency then is based off of 1 second. So sometimes people get kind of confused. When I'm doing my period, I'm talking about how long does it take to complete one cycle. And then when I'm talking about my frequency, I'm talking about how many cycles it is to do in 1 second. So for example, this one, my 60 hertz then is doing it 60 times in 1 second. My period, it takes 16.67 milliseconds to complete one cycle. All right, everyone still following along with the frequency and period? All right. Gets to be a little confusing and stuff like that, but we'll get, it'll just come natural after we do that. And I kind of put up all those, little reminders, cycle, one complete waveform before it repeats itself, period, time for one complete cycle, frequency, number of cycles in 1 second. And then I give you some of the formulas. Period is equal to 1 over the frequency, and then frequency is equal to 1 over the time. Let's see. All right, so let's take a look at, let's see if we can find a good image here. So look, I'm going to just go to page 336 here. I'm just using the image bank off these, so I don't have to draw up all these things every time. So I'm on page 336 here on figure 8-12. And we'll use this one for looking at all our different measurements. So now I said that so if I'm describing something that's in DC, I can say that it's 5 volts, okay? Or I can go, I want to make sure that I'm very clear on what I'm saying is that it's 5 volts DC, okay? If I don't see any units behind it, I'm always going to assume that it's going to be a DC voltage. Because we can have DC voltages and AC voltages all over the same circuit. So we can either do it 5 volts or 5 volts DC. Now if I'm talking AC waveforms, now I have to be very specific on what I'm talking about. So for example, on this one here, we have an 8 volts peak. I have to write it that way. So I'm going to have to, I don't necessarily need to write the polarity of it at this time, but I do need to be very specific. I got to make sure that I write it as 8 volts peak. I'm just going to represent it with 1 P. Another way of looking at this signal too to describe this signal is that so 8 volts is from where it crosses it's not so much where the 0 is, but where is the DC reference. Okay, so my voltage peak is based off my DC reference to how many volts it is above that DC reference. That's going to be my voltage peak. My voltage peak is also described from how many volts it is from my DC reference and how many volts it is away from that DC reference. That's also going to be my voltage peak. So this can either be positive or negative, and we're just describing that. It's going to go 8 volts above the DC reference, and it's going to go 8 volts below it. So if I just write in 8 volts peak, I'm already describing that. I know that it's going to be 8 volts above the DC reference and then 8 volts below the reference.
Could you do like plus or negative 8 volts? Would that work?
No, not when we're talking about just voltage peak. But what we're going to see, so if we wanted to, if we're really trying to describe it, and we don't know where that DC reference is, so we might not know where the DC reference is at. So then what we're going to be using is our, so this one here that I would describe it as, it's going to be a positive 8 volts max, and it's going to go down to a negative 8 volts min. So when I'm using V max and V min, then I'm going to use my polarities. Okay? And then based off of that, then I can figure out what my DC reference is, and we're going to look at that as we get going into this chapter here. I've got a little worksheet for you. So yeah, so when we're talking about V min and V max, then we're going to be using polarity. If I'm just talking about 8 volts peak, I've already known that I'm going to be 8 volts above my DC reference and 8 volts below my reference. And that gets to be a little bit more complex too, but you'll see that when we start talking about our V min and V max and all that. Now another way that I can describe the same signal is that I can tell to go that it's 16 volts peak to peak. So I can write the same one down as 16 volts peak to peak, meaning that it's going from here from where it's going to the maximum amount of voltage down to my lowest amount of voltage. That's going to be my voltage peak to peak. And it's always going to be, my voltage peak is always going to be half of what my voltage peak to peak is. So if I don't describe what I'm looking at, if I'm all of a sudden, if my unit's on my circuit, and depending on who's designing the circuit, they might call it, they want an AC signal, and they want it at 8 volts peak at 1.2 kilohertz. Okay? So what we want to do is have a signal that looks very similar to this, and I'm going to do it at 1.2 kilohertz, or I'm going to do it 1,200 cycles in 1 second, or 1.2 kilohertz. Now another engineer, he might describe it as being, I want it as 16 volts peak to peak at 1.2 kilohertz. I would set up the function generator the same way. This and this are both the same. They're both the same amount of values. It's just how we're describing that waveform differently. And then that also goes true with current too. That can be, my current can also be, I have my current peak, and then I also have my current peak to peak. So that goes true with both either the current or my voltage. Whatever is specified on our data sheets or our sheets or our drawings, if one engineer calls it out that he wants 8 volts peak at 1.2 kilohertz, then that's what all our calculations are based off of. So if I wanted to find out what the voltage drop across R1 is here, then I would have to keep the units the same. So I always want to keep my units the same so I never get confused with what's going on. So my voltage drop would be 8 volts peak at 1.2 kilohertz. Another engineer, he calls it at 16 volts peak to peak, 1.2 kilohertz. Then I would want to calculate all my voltage drops and everything else using my peak to peak formula. And then everything else stays the same too. My current then would be calculated out, you know, depending on what my resistor value is, what my current, then my current would also be in peak value. So you got to make sure you keep all your units the same. All right, then our next, our other unit then is that we can also call it, we can also have an RMS value. Now when I said that, for example, this outlet, I said that it was 120 volts RMS, or 120 volts AC. What I'm talking about is that that's an RMS value. So the RMS value, so this is another unit that we can classify our unit. So for example, the RMS value is the heating effect of a resistor. So for example, we'll stick with, we'll use it since our common AC voltage is 120 volts. So for example, if I hook up a function generator or I plug a resistor into my wall, I'm going to get 120 volts AC going across that resistor. And that resistor is going to heat up a certain amount of time. It's going to heat up to a certain amount of temperature. If I were to put a heat gun on it, this thing might, let's just say that, let's say it goes up to 175 degrees. That resistor is going to heat up to 175 degrees when I have 120 volts AC applied to it. And when I'm talking about heat, that's what we consider, that's my power, right? That's some type of a power. I'm producing either heat, light, or something. So it's producing heat coming off that resistor, and it's going to heat it up to 175 degrees at 120 volts AC. That resistor, the same resistor, hooked up across a DC voltage supply, I can hook that up to 120 volts DC, my direct current, and that resistor would heat up to the same amount of temperature. It would heat up to 175 degrees. That's my RMS value. That's the amount of heat that's being produced by a component at the same voltage. At 120 volts AC, I'm going to heat that resistor up at the same voltage as 120 volts DC. But now if we look at that 120 volts AC, and let's really take a look and see what that voltage is across that AC. Got 120 volts AC, and so that means I got a AC waveform. And what's happening on this resistor is that at 0 volts, that resistor is not heating up anything. And then as I start to increase on my amplitude, and I start getting up to my 120 volts AC, now that resistor is really heating up. It's going to heat up to its maximum. And then as that voltage starts to decrease, this resistor is going to start to cool off. Then when it gets to 0, that resistor is going to be turned off. It's going to start staying cool. And then all of a sudden it's going to start to heat back up again as I go to my negative side of my peak. Now the resistor is going to start to heat up to its maximum amount again. And then it's going to start cooling down. And if I average that out, I'm going to get a temperature, we'll just say approximately 175 degrees. If I have 120 volts DC applied to it, I'm constantly applying 120 volts DC to it. That voltage isn't changing, it's just 120 volts. And it's constantly, it's not heating up and cooling down. It's always just going to heat up and it's going to stay at 175 degrees. So it seems strange that I can have 120 volts AC heat up the resistor the same amount of 120 volts DC. But if I really analyze what an AC signal is that because I'm not using the units, if I calculate it out to figure out what my voltage peak is, and on the bottom of that page of 337, they're giving you the RMS value. The number that we use all the time is our 0.707. So if I want to know what my peak voltage is of an AC waveform is that I take 120 volts Yeah, and divide by 0.707. And what do you end up getting? So if I take 120 volts and divide by 0.707, what do I get for a voltage? Yeah, so I'm going to get, so this thing is going to go up to a positive 169.7 volts peak. And then it's going to go down to a negative 169.7 volts peak. And if I times that by 2, then I realize that my voltage going across this AC signal is actually 339.5 volts. Peak to peak. And make sure you stay keeping your units, okay? So now, you can see that we have all these different units now. I never changed my voltage source, but I can describe the signal in many different ways. I can call it that it's 120 volts AC, or I can say that it's 169.7 volts peak, or I can say that it's 339